So let me start by introducing myself. I'm Freddy Cachazo. I work here. I'm a researcher here at Perimeter Institute. And this week, or these 4 days, so this was a short week, but we will find a way to make up for it. Don't worry about that. This week, the idea is to discuss quantum field theory. Everything there is to know in 4 lectures. Well, quantum field theory is 0. Actually, I want to give a different name to this. Perhaps my friends in Quantum Foundations will completely kill me for this, because this has a completely different meaning. Well, not completely different, but a more rigorous meaning. But I decided to give a different name from the standard one, because we're going to basically start from a very different place from any book that starts quantum field theory. And why are we doing this if you have a quantum field theory course later on? Well, basically this week is some sort of warm-up, okay, for what's coming next week, which are your first 2 core courses, okay, relativity and quantum mechanics. Now, the reason I want to start from a very different place than the usual books is something that happened last year. In the summer, something spectacular happened. Does anybody know what happened? Excellent. The Higgs was discovered. So that's a big triumph for humankind, right? I mean, this is something incredibly spectacular. That a set of equations so simple as a standard model, well, at first, they don't look that simple, okay? But if you think about it, it's something completely spectacular. We human beings, we can write down something that describes nature to incredibly short distances. And everything seems to work perfectly okay. Hundreds and hundreds of experiments carried out, hundreds of thousands of measurements, and everything fits perfectly. So what are the measurements we do? So that's why I decided to start with collider experiments. In particular, we can keep in mind the Large Hadron Collider. Which was the start of the show last year with the discovery of the Higgs. Okay, so what do we do in collider experiments? Well, we usually have 2 beams of particles, and we make them collide. So that sounds very easy. So let me represent one of the beams. So we have a bunch of particles. Of course, this doesn't look very nice. So people like to draw this as if it was a cylinder, an imaginary cylinder containing the particles that we're going to scatter. They are moving with some velocity. And in some frame, we can think about another bunch of particles as particles that are at rest. Okay? So these ones will be our target. And these are somehow our projectiles. Okay? So we're going to throw all these particles and make them collide with all these particles that are sitting here. Okay? I had a hard time deciding how to call these things. So how to say, well, the target should be T, and the projectiles P, or so. In the end, I couldn't come up with a nice notation for that. So we're just going to call the particles here particles A and particles B. Okay, for the lack of a better name, that's what we're going to do. Of course, in different frames, we can think about the 2 groups of particles as moving and colliding. Okay? So for particles that are in the set B, we have some density of particles, rho B. Our bunch of particles, let's say it has length B, and the same thing for particles of type A. Okay? Very good. So what happens? We're going to make these things collide. I'll also assume that these bunches of particles have an area A. Okay? Somehow we make these cylinders of particles, full of particles, and make them collide. How many particles per cylinder we typically have? Well, I don't know in general, but I know I check in Google, and the LHC has per cylinder, if you wish, 100 billion protons. Okay? So we're talking about two bunches of 100 billion protons coming together, colliding, and doing stuff. Okay? In fact, the LHC scatters 3,000 bunches of this sort every time against each other. Okay? Now, these particles come, or these bunches of particles come, they mix with each other, and particles come out flying. Okay? They are the result of one particle from A and one particle from B colliding, okay? But we have tons of them. So we have a lot of statistics, right? Because we have billions of particles colliding. Now, what are we interested in? Well, our detectors will tell us the kind of events that happen, okay? So we're interested in understanding the number of events of a given kind. Now, what could this dependence, the dependence of the number of events of a given kind, on the parameters we have on the top blackboard could be? What do you think? So that's the object we want to compute, but we want to somehow strip out all the information that comes from the actual experiment we're doing. Say, the kind of collider experiment we're performing, the size of the object, and so on. So we have to strip out all that information. In order to do it, and to get something that is more intrinsic to the actual physics that is happening, particle per particle, we have to find out how this thing depends on all the parameters of our collider. Okay? So how does this depend on, say, the area of the bunches? Should be proportional. Excellent. How about on the other parameters? That's right. It should be proportional to the density of the particles in the target, proportional to the density of the particles that are approaching, the length of the beams. Okay? That's pretty good. Sorry? Proportional to the number of particles you have in the beam. That's right. That's right. So that information is here, and we're going to write it like that. Yes, we're going to have the area squared. That's going to appear. But the number of particles, so let's actually write it here. The number of particles in the target is equal to what? And the number of particles that are approaching, that's right. So in terms of this, the same formula can be written as oh, you're happier. Excellent. Well, actually, this is the formula I was going to write next. So that was very good. But so all the physics that we want to extract out of this is in whatever we have to write here. So if this is dimensionless, what should be the dimension of the thing I'm going to write here? Well, it's trivial now from this formula, right? What should it be? Dimensions of area, yeah. And it's usually denoted as sigma. So this object has dimensions of area. And this has special units in particle physics. You can also try to Google to find in the internet why this is called a barn. Okay, I think there are several funny stories about this. But it happens to be 10 to the minus 24 centimeters square. Okay? Okay, if you find a funny story about why is it called barn, you can tell us tomorrow. Okay, that's pretty good. So this is a formula we want. Yes?
I mean, should be there some dependence on the velocity of the beam as well?
Yeah, all that dependence will go in here.
It's going, okay.
Yeah.
We've already specified that this is the number of events of a given time per unit time. Then you don't need to talk about velocity.
Well, this is the total number of events in this experiment that I'm carrying out.
In the total
Yep, these things are these bunches of particles. These are not happening all the time. Not even at the LHC. The LHC produces bunches of particles. Then they go around the tunnel, collide, and then they inject more, and then they inject more, okay? Very good. Yeah, at some point, I should start using the presettings. Okay. Very good. So before the LHC, there was another collider, actually in the same tunnel, called LEP. This is a large electron positron collider. So does anybody know what a positron is? It's the antiparticle of the electron. Very good. So we know what it's called, right? So there is a particle called the antiparticle of the electron. That's pretty cool, and you can use it in parties when you go and tell your friends. But probably not in this course, but in today's tutorial, you will learn what, what the positron is, okay? But for the time being, let's just say that the electron is usually denoted as E minus, and the positron is usually denoted as E plus. So LEP, from LEP, we could compute the cross-section. So, of course, if it's called a large electron-positron collider, it's because we are colliding in one bunch of particles are electrons and the other bunch are positrons. The LHC collides protons and protons, okay? So this cross-section of taking, oh, I didn't write it. That somebody said it, right? This is called the cross-section. Okay. So at LEP, people measure the cross-section of E plus, E minus going to, say, mu plus, mu minus. What is mu? Does anybody know? The muons, that's right. These are muons. They also measure the cross-section of E plus, E minus going, say, to mu plus, mu minus, and gamma. What is gamma? It's a photon. That's how we denote photons. But they also measure the cross-section of this happening. Of producing a mu plus, mu minus, and two gammas. And you can guess what happens next. You can also measure the cross-section of producing two muons and three gammas and so on. Many other things can happen. You can measure the cross-section of this going to taus, to towns. And of course, you can also measure last but not least, the cross-section of producing, again, E plus and E minus, okay? So all this is happening, and all these numbers can be measured. Now, our job as theorists is to find a theory that computes them and predicts them. So that sounds easy, okay? At least we didn't have to build the accelerator. Yes?
One question, how can you determine if what you're measuring, for example, for the process of having one photon differs from the one of two photons?
Yes. So, of course, if the two photons, that's a very good question, if the two photons are very, very collinear to each other, meaning their momenta are very parallel to each other, it's impossible to distinguish them. Very, very hard to distinguish them. Here, what I mean then is what happens when the photons are in different directions, okay? They come out in different directions. But that's a very good question because just the cross-section as I'm giving you doesn't really do justice to what the detectors can do. Detectors not only can measure what kind of events we get out, but they also measure the momentum of the particles coming out, okay? And nowhere here I told you anything about the momentum of the particles. So there must be a more refined observable that knows about the momentum of the external particles. Yes?
So how do the detectors tell which particle is it based on mass and everything?
Yeah, so the detectors will have different tricks to tell particles apart. So they will have different materials that can absorb very easily different kinds of particles. They will have magnetic fields that can deflect particles to tell their charges. They will have tons of tricks. But I'm happy I don't have to know them. Yes?
That's not an exhaustive list, but shouldn't the first thing that happened be E minus E plus just goes to 2 gamma and nothing else?
Well, this is not as you said, this is not an exhaustive list, yes. So we can have tons of things. Actually, measuring, yes. It's much easier, I think, to measure things like this. Well, it depends on what you want to do. So you design your detector so that you measure is optimized to measure a particular thing, okay? Very good. So let's see. As we said, we want to have something that does more justice to the detectors. So you can also find in the internet, I encourage you to search for Atlas and CMS. These are the two main detectors at the LHC, okay? And study very carefully how they work. And then come back and explain it to us. So, as I said, not only they can measure which particles come out, but they can also measure their momenta. Okay? So if they measure the momentum of the outgoing particles, we can try to define an observable that depends on that. We can try to count how many particles were produced of a given kind in a given region in momentum space or in the phase space, what is called the phase space of the external particles. So the space of all possible momentum configurations of outgoing particles is called the phase space. Okay? Now our job right now is to find how to determine an infinitesimal volume of that phase space, okay? Because we want to define an observable that depends on or counts how many particles are measured in an infinitesimal volume in phase space, okay? So that's what we want to do. So for each of the external particles, as I said, I couldn't find a good notation now, even for the external particles. So say that outgoing particles will have momenta denoted as P1, P2, and we will allow any number of them. Okay? So whenever you see numbers 1, 2 through n, at least today, that would mean that these are outgoing particles. Yes?
So this name phase space is slightly different from what in the sense phase space in classical mechanics. That also includes the position of the particle.
That's true. Yes. So we're going to define it actually. Yes. So we have outgoing particles. Okay? They have this momenta. Their momenta is described by 4 vectors, of course. Now, what is the space of all possible configurations of momenta for n particles? What would you say? So those who are mathematically inclined, what kind of manifold would that be? Or which manifold would that be? So our first approximation could be that our phase space must be perhaps, okay, or naively, looks like R for n. Okay? But that's nonsense, of course, right?
Why R4N?
Okay, so if you're really picky, it should be R n comma 3n. Yes, it's 1 per particle. Yes. Okay, but that's even the next one is nonsense. Yes.
Can you not have like just like n, 3n, and then plot it for each of the n particles along one axis? I mean, like the t component x, y, z for
Yes.
1 to n, and plot each of those on the axes. Why
Sorry.
do you have?
I'm just telling you, if I didn't know anything else, the space of all possible values of these objects happens to be that, right? But we know better, right? We know these are particles, right? If they are particles, well, we haven't defined what a particle is, by the way, right? But we will. So for the time being, let's use our intuitive notion of what a particle is. And we all know that the most fundamental thing that we assign to a particle is its mass, right? So if these are particles, they all come with a mass. So are we allowed to have any values of the momentum? No. So you're saying no. So why? Very good. So if these are physical particles, they have to satisfy the following equation. So P for particle I, okay, so that's my notation for the ith particle. The norm of this vector has to be equal to the mass of the vector square, okay? And this is called the on-shell condition, okay? So we are working, or we're going to be working on, I'm giving the lecture, so I choose to work with a metric that is mostly minus. Okay? So in this, with using this Minkowski metric, pi squared happens to be, I mean, people usually denote the first component, or we, I mean, as if I didn't. The first component of the vector is going to be the energy. So that's what I mean by the norm square of the vector. Okay, very good. So why is this thing called on-shell? What do I mean by that? Well, in the meantime, let me also ask you something else. So is the mass a Lorentz invariant? Yes, people say yes. Excellent. Yeah, so here, course, when we are in high school, sometimes people tell us that the mass can change and this and that, but we're not in high school anymore. So we know that when people talk about the mass, we only talk about the rest mass, and this is a Lorentz invariant, okay? Because it's defined as the norm of this vector, in fact. So it's a Lorentz invariant. Is there any other Lorentz invariant that we can construct for each particle? Yeah, but out of the things that I have here, so we said that Lorentz invariance. Yes, but just for one particle. So we said that the mass is a Lorentz invariant. But there is another one that is really tricky. It's also hidden in the momentum of the particle. It's actually the sign of the 0th component of the momentum of the ith particle. Weird, huh? Well, why is this Lorentz invariant?
That's in the case you use that metric, or it's,
No, it doesn't matter.
doesn't matter if
Yeah.
I change just the sign to the -1 up there, it's also Lorentz invariant.
Well, no, but it's a sign of the component. This is different from the sign of that component, right? Yes. So why is this true? Well, to understand that, let's actually draw what we mean by something being on shell, okay? So it's convenient to consider the case when the mass is 0. So if the mass is 0, we can draw in momentum space we can actually draw a cone okay? This is in momentum space. And a particle that has mass 0, its momentum should be constrained to lie on the shell defined by the surface of the cone. Yes?
What's the pi tilde over there?
What is the
The
P?
mod pi?
Oh, so there is a 3 momentum, right? So we have the vector P, which is defined as Px, Py, Pz. And that's the norm, yes?
Is the sign of the 0 component of the momentum, is it only invariant under a certain component of the Lorentz group, or is it under all invariant under everything,
Very good. It's only invariant under,
like the other?
yeah, only under the connected component of the Lorentz group, yes. Okay, so particles with mass will then be restricted to lie on hyperbolas. So the momentum has to lie somewhere here, okay? Now the sign of the 0th component tells us whether you are future directed or past directed, okay? Of course, if we have a particle, not that we have, but suppose that we had a particle whose momentum could be outside of the lie cone here, of this null cone, then its 0th component would not be Lorentz invariant. The sign will not be Lorentz invariant because a Lorentz transformation could move you up and down. Lorentz transformations cannot map a point that is inside the null cone to a point that is outside. In particular, it cannot map a point that is pointing in this direction to a point that is pointing in this direction, to a vector that is pointing in this direction. And that's the reason the sign tells you if you are on the top half or on the bottom half. And Lorentz transformations will not be able to map you from one to the other. So that's why it's Lorentz invariant for physical particles, okay? Not for unphysical particles. How can we call, do you know how it's called a particle whose momentum is somewhere here? People have given a name for such a weird thing. It's what? A tachyon. Yeah, that's right. But that's not important for us because, yeah. Okay. So we're ready for our second approximation to the phase space. Okay? So we want to define the volume of an infinitesimal region in phase space. if this was a phase space, the infinitesimal volume element would be just this, right? But we know it's wrong, so we have to fix it. So knowing this, we should impose, I'm not going to try to describe what the phase space is as a whole, because it's a very complicated manifold. It's a submanifold of this one, and it's a very curved manifold. Instead, I'm going to try and modify the infinitesimal volume correctly to get something that is correct. So the infinitesimal volume, or our second approximation, so this was our first approximation. Our second approximation is that it should be the product of all these particles constrained to have their momentum on the mass shell. Okay? But these are outgoing particles, so I want everybody to be outgoing. So I'm actually going to put here something that constrains the sign of the zeroth component, where this is defined to be 1 if x is greater than 0, and 0 if x is less than 0. Okay? What do you think? Are we done? This looks quite reasonable. Do you think that that's the whole space available for us? Remember, that's what we're trying to describe. All the space that is available for our external particles to go into. Excellent, very good. Imagine that our initial particles, the sum of their momenta is square, is some given quantity. Okay? Well, can we access the whole space of external of outgoing particles? No. We have to preserve momentum. We have to impose momentum conservation. So our final approximation, which is approximation 3, is that the volume of the phase space is corrected by simply asking the momenta to satisfy momentum conservation. So the sum of the momenta of all the external particles must equal the sum of our incoming particles. And now we got it. Okay? So that's the space available for us. And we want to ask, is this going to work? And we want to ask, what's the probability, or how many events happen to lie on a given differential of the volume of the phase space? Okay? Now, this quantity here has a name. It's called the differential of the Lorentz invariant phase space. Okay? So you will hear people talking about the D-ellipse. Yeah, you know. Okay. So now we are ready to define the object we want to study, which is called the differential cross-section.
Question.
Yes?
So we're assuming that the momenta of all the incoming particles in the two bunches are identical, right?
Yes.
And that is what PNT.
That's right. Very good. Thank you. Yes. So we're assuming that, well, just from the picture, right, the target, say, is not that they are at rest, and the ones that are incoming, they are all, that bunch is incoming with some velocity. And then that means that, yeah, said another way, we're also assuming that all the particles in that bunch and all the particles in this bunch are of the same kind. Okay, we're not mixing electrons with protons. We're only throwing electrons against positrons or throwing protons against protons. Okay, that's a good question. So we're going to define the differential cross-section, okay, just as we did there, but now with our d-libs. Now it's a differential cross-section for particles A and B going to some external state whose Lorentz invariant phase space element is defined in this way, okay? And of course, we need something here. How do we know that we need something here? There are two reasons. We are still missing something in this formula. Yeah, first of all, dimensions. Second, this thing, according to its name, is a Lorentz invariant. And this is an area. So this is wrong at the moment. Not only that, this object is only knows about the kinematics of the process, and it doesn't know anything else. So this cannot be the full answer. So let's fix one problem first, okay? Let's fix the problem of the fact that this is not Lorentz invariant and this is Lorentz invariant. So the problem is going to be fixed by, actually,
One thing.
yes.
You say it's Lorentz invariant. I see why the on-shell constraint and the sign constraint are Lorentz invariant itself, but the delta of the total momentum is also Lorentz invariant.
Yes, so imagine you perform a Lorentz transformation on a delta function of that sort, right? Then an exercise for all of you, which you should try, is that in order to undo the Lorentz transformation, the only price you pay is the determinant of the transformation you perform, okay? And the determinant happens to be 1, because the Lorentz group is SO 3,1, which you all know from Anna's course, I think. If not, well, it doesn't matter. Tomorrow we will discuss something. Okay, so we have to fix this. It turns out that the object that we want to put in here, after all, we took into account the phase space of the outgoing particles. So the object we're going to put here is something. The numbers are conventions. But this is something that depends only on the incoming particles, or the particles we're going to scatter, okay? They are the energy of the incoming particles, the product of the energies, times the magnitude of the relative velocity, okay? So now an exercise for you is to show that this object has the same Lorentz transformations as an area, okay? So check Lorentz transformations. So if this takes into account the Lorentz transformations, what we're left with is something that is Lorentz invariant. So this D is Lorentz invariant. And it contains all the information of the dynamics. That's why I call it D, okay? Everything else is just kinematics. So all that has to do with the physics of what's going on in the interaction has to be contained in our object D. And that's what we're going to study for the rest of today and most likely in the remaining of the lectures. Okay. Now, we have seen that we produce, scattered in the same particles, we can produce many different things, okay? So that tells us that whatever is governing the physics of these interactions must be probabilistic in nature, okay? Yes?
So
No. The factors are the yeah, very good. Sorry, the numerical factors.
But energy is transformed the right way when you put them on the bottom.
Yeah. So the claim, what you want to check, or what I want you to check, is that the product of the energies times V compensate the Lorentz transformations of the left-hand side. Okay. So that should be a fun exercise. Right. So I was saying that in order to compute D, is where all the dynamics and all the physics will enter, right? So in order to do that, we have to take a small detour. Okay. So, but before we attempt to do that, let's take a small detour and review some features of quantum mechanics. Okay? Yes?
So D is a dimensionless constant here, and why do we choose it?
No, it's not dimensionless.
It's not? So why do we have the factor of 2EAEDV? Why could we not just have a big overall?
Well, just to determine the dimensions, just look at the, you should look at the dimension of the D-ellipse, okay? That's an exercise. For any number of particles, try to determine what the dimensions of every factor here is, okay? Just look at the D-ellipse definition. Okay. So let's do some quantum mechanics. Very, very basic quantum mechanics we're going to do because you're going to have a course on that. Yes?
I'm sorry, what's the character after ED that's in magnitude parts? D.
Yeah, I somehow erased that there, yes. Okay. All right, so what do we want? So in order to describe a quantum mechanical system, we start with a Hilbert space. Okay? And we can have some bases for our Hilbert space. So roughly, we can think about this as a vector space, and we have a basis of the vector space. Okay? But in principle, we can have different bases. So somebody can choose this, and another observer can choose a different basis. Okay? So these are two different bases. Let me call this B and this B prime. Now, for them to describe the same physical reality, Wigner, in the 30s, found what the condition had to be, and the condition is basically the following. There is a more refined condition, but we're not going to discuss it in this. We only have 4 lectures after all. Actually, 3 and a little bit. So there exists an operator, let's call it U, that maps one set to the other set, okay? So if you have a state psi, there will be a map to state psi prime equals to u acting on psi. Okay? So Wigner told us what this operator has to satisfy, and that's what we're going to get. Right now. Yes.
I don't know, maybe this is really pedantic, but shouldn't, when you have the different bases, shouldn't the label, the index, I be I prime for this B prime basis? Because if you're keeping the indices also independent of each other?
Yeah, you're right. It's very pedantic to do it. Yeah. So we're not going to do it. So, very good. So what happens? So imagine you have a state psi, right? A general state expanded in the basis psi I. Okay? So the physical quantities, and this is a basis that diagonalizes some observable. Okay? So the physical quantities we want to compute are given by the probabilities, say, of finding our state psi with an eigenvalue that corresponds to the state, to the basis psi I after we perform a measurement, and that number is this, which can be computed from there by assuming that the basis is orthonormal by this quantity. So these probabilities should be preserved. Okay, these are the physical observables. And that means that we will like, when we apply this transformation to our psi prime states, we should get the same answer. But these states are obtained by applying this transformation to the original states. Okay? So before we can learn what U has to do, we should review a little bit of what the adjoint operator is. The adjoint of an operator O is. So if we have an operator O with matrix element given by this, in other words, is sandwiched between two states, we define the adjoint of this operator to be the following. It's equal to this. Is everybody familiar with this? You're all happy with this? Excellent. Very good. Or, in other words, we could think about this, okay? So if you see this, this tells us that we can think about this as the operator acting on this state phi, but the star tells us that we can revert this and think about this as O phi psi, okay? So this is another way of thinking about what the adjoint operator is. And now we can use this definition to apply it here and discover that if we apply that definition here, okay, we can undo this, go back, and write this as psi I, put the adjoint of the operator for this half. On this side, we just apply U to psi. And then getting the equality tells us that this product has to be 1, okay? Yes?
Or times a phase.
Times a phase. But then, to understand what the phase has to be, and to understand that this can be unitary or anti-unitary, which is the other option, you have to read Wigner's paper, and I encourage you to do that. So he found that we need this operator to satisfy the following. is a unitary operator. Okay. Yes, sorry. Okay. So now we are done with our small detour, and we can go back to scattering physics. Okay, so we're going to have some working assumptions. The first one is that all the physical world, or at least the physical world relevant to the scattering process we're going to study, is described by a Hilbert space. Second, the set of all incoming particles of all possible forms, or better said, states, forms a basis. Okay? Now comes the tricky part. How do we even define this? Well, I'm going to define this as follows. I'm going to declare that there is one state that is a vacuum, meaning no particles at all. So that's why I decided to replace particles by states, because you would say, somebody would complain and say, look, you did the vacuum, it's not strictly speaking a particle. The direct sum of this, of the vacuum, with all possible states that represent a single particle. Okay? So this is called the set of one particle states. Plus the set of states that represent two particles. This is what we have been discussing up to now. Okay? Our incoming particles are described as just a state in the sector that describes two particles. Okay? These are the two incoming particles. But nothing really of what I've discussed depends on the fact that we only scatter two particles. We should be able to describe more particles if we wanted. So we can have three particle states. And in fact, we need an infinite number of sectors. Okay? So this is one basis of the Hilbert space. We're going to end when we, let's see. Yeah, that's right. It's a natural place to stop. Let's continue here. So here comes something very tricky that in different books you will find it described in different ways. But I think this is the next assumption, or what I'm going to tell. Yeah, the next assumption is the way I would like to phrase it, which is that the same is true for outgoing particles. Okay? So we have only one Hilbert space that describes all the physical reality. Okay? Now, I'm assuming that all the set of possible incoming particles form a basis of the whole Hilbert space. Okay? I'm also assuming that there is another basis, which is made out of all possible outgoing particles. Okay? So you see the consequence of this, which is easy to state, is very profound. It means that a single state of the outgoing particles can be expressed as a linear combination of the states in the incoming particle basis, right? After all, they are both bases. So to distinguish the bases, I'm going to give a label in to these ones, and to these ones, I'm going to give a label that it says out. Okay? So as I said, in our experiment, in our case, we have some particular external state. Remember, we call them P1 up to Pn. Those are our favorite particles in the final state. And the fact that these guys form a basis means that this state can be expanded in that basis, okay, of some other momenta. Let me call them P prime to distinguish them from P. In fact, we have to integrate over the d-ellipse of the corresponding m particle states with some coefficients. So let me put the coefficients here that depend. This will depend, of course, on the incoming guys, on the choice of the outgoing guys. Let me call them final and incoming in order not to, or initial, in order not to write too many things. Okay? Very good. So whatever we want to compute, this D that we mentioned before, our physical object, must somehow be related to the following: to the overlap of our initial states, PA, PB, and our final states. Okay? So whatever this quantity is, somehow must contain the information we need in order to compute the dynamical quantity that enters in the cross-section, which is the thing we measure. Yes?
I think I'm a little confused about that point. So does that suggest that we don't have a definite number of particles?
Oh, brilliant. That's right. It means that, well, no, I didn't say that. Sorry. I said these are all possible experiments you can ever perform, right? Which don't necessarily involve only two particles. Right? So the experiment in the collider that we're actually doing only contains two particles. And that's why we are only dotting this external state with this particular state. Yes?
So what is the subscript on the coefficient?
The subscript in the coefficient. Oh, here. Oh, I didn't want to write everything, so I just wrote final and initial.
What does it actually mean?
Well, it depends. It's a coefficient that depends on this, and this coefficient depends on this. It's just like what I did when I expanded the bases. In fact, the alpha here should have a label that depends on the state psi, right? If I really want to keep all labels correctly there. Yes. Okay.
What does it mean to have a linear combination of one particle state, a state with a three particle state? I mean, the sum of both states.
That's a good question. Yes, sorry, just a second. But in fact, these are all of them are just states in our Hilbert space, okay? So that is a completely fine, I know it sounds a little bit strange because in quantum mechanics, in the standard quantum mechanics that you have seen, you always have a fixed set of particles, right? But precisely, one of the things we have learned from the experiments, right, is that we can produce, from the same two particles coming in, we can produce a variety of final particles. So we are forced to introduce a Hilbert space that contains all these states together. We have to treat them all together, okay? Yes?
So are we considering two different Hilbert spaces? I guess I'm confused because it seems like that.
Yeah, some books will tell you that you are considering two different Hilbert spaces. But the way I'm telling you is that there is only one Hilbert space that describes nature, and it has a basis of in states and a basis of outgoing states.
So I guess I'm a little bit confused because with the direct sum notation, it seems like all the two particle states and all the three particle states should be orthogonal. So that product should always be zero.
No. This is a different basis. I'm calling them out, okay? It's a completely different basis. In fact, now we're going to answer that question. So if these two are different bases, okay? I mean, to be strictly formal, and which is something we're going to do when we do the quantum field theory course, right? These are states that have the profile of particles in the infinite future with this given momentum. And this is a state that has a profile of particles in the infinite past that have this momentum. Okay, we really have to work hard to make this very, very precise. Okay, but for the time being, I don't want to be that precise and simply say, well, we have these two bases of objects. If they are bases, we look at our quantum mechanics review and say, well, there must be an operator that maps one basis to the other. Okay? So their message is an operator. I'm going to call it S for scattering. That does the following. It takes our states or maps one basis to another basis. So using this quantity must then be the matrix elements of this operator in any of the two bases. So I choose them to be the in bases. So the relevant physical object would be the matrix elements of this quantity in one of the two bases. Okay? Very good. So let's see. Okay. We're almost there to actually tell you what D is. So that's where I want to finish the lecture. I want to tell you exactly what D is in terms of this.
Does the scattering operator is just defined for the same number of particles?
So remember, our Hilbert space is a huge monster, right? So in fact, the Hilbert space not only is infinite dimensional, right? The space is not even countable, right? Because it has states for different momentum, and the momentum can take continuous values. So we have this incredibly large space. The S operator is an operator that acts on that space. So using the name matrix is a little bit of a stretch, right? But if you think that you could, in the finite dimensional case, we could arrange the vectors in a countable set, right? And then define a matrix as the contraction of our operator with different entries, with different bases, right? And define matrix elements and build a matrix, right? So we want to borrow that language and say that these physical objects are the entries of a matrix, okay? So was that your question?
Should it be always a square matrix?
Oh, no, this is one entry. I mean, this is one entry of the matrix.
I think the question
So,
because the second last line has n on both sides.
so look at the vector space, right? At the Hilbert space. Think about each of those vectors as one entry. Of course, we cannot label them as 1, 2, 3, 4, right? Because they are uncountable. But we should think if we could do that, each one of those guys could be one of these psi's, okay? Psi I. So you should think about this as a contraction as the matrix elements of S dotted with some state psi I and some state psi j. It happens that this state psi j is this one. It so happens to be this one. And this one happens to be this one. Okay? But they are all states in the Hilbert space. Okay? They should be treated in the same footing. Yes?
Right. I think the question is that do those ends necessarily have to be the same on your out? So you have S hitting a state with n particles and then coming out with n particles. Can those be different? You have different numbers of particles on both sides?
No. This is the same.
They have to be the same.
Yes.
Well,
Yeah, I'm defining the operator in this way.
that's your definer.
Yes. Okay. So we're almost done. All we need is to realize that that object that's given has pieces that we are not interested in. So the S operator so what's the best way to say this? So what do you think we should use for an operator that tells you that no scattering happened? So the incoming particles just miss each other and just fly by. Should be the identity, right? Very good. So if we're interested in scattering, we should really subtract from here the case when nothing happens. That's the identity. In fact, if you put the identity here, in this particular case, we will get 0, because these two states are orthogonal. Okay, so if you put the identity, it doesn't matter if we put it or not here, if we subtract the identity, because this will give you 0 in this particular example, right? Yes?
Something with respect to that. So you're defining your states to be orthogonal if they have a different number of particles and also different...
Even different moment, yes. Yes.
Sorry, how do we know they're orthogonal?
Because I'm choosing my final states. I know what I want to see, right? They are different. By assumption, they are orthogonal. Because they are bases. They are on orthonormal bases. Okay?
But
Pretty good.
That's a different set of that's a different basis, and that's a different basis. So why would? Oh, it's in and in. My bad.
Yes. Okay. So I'm going to give a name to this operator. It's called IT. People put the I just by convention. So this is convention. Okay? And then say that we are interested in are the matrix elements of T okay? I'm going to drop the in, assuming that we know what we mean. Now, this object, okay, this object must know that if we scatter, or if we try to scatter states that the total momentum doesn't agree, we should get 0. So this matrix element somehow should know that there is a delta function imposing momentum conservation. And whatever else is left here is usually called M, and it's called the invariant matrix element. Of the process PA, PB going to P1, Pn. And now we are ready to finish the lecture because it turns out that the object we need in order to describe our differential cross-section, cannot believe it, did I erase it? Yes, I did. That's really bad. Well, at least I defined what I wanted. Our D happens to be the mod square of this P, of this M. Okay? So, if you found many things during the lecture confusing or unclear, that was the purpose. In fact, given the nature of the course, that is very fast-paced, many people will come and tell you about different subjects, very interesting subjects, sometimes at the cutting edge of research. And by nature, many things will be unclear, and it's your job to try and fill the gaps, okay? In this case, these 4 lectures are just, as I told you, a warm-up for what is coming. We will have a quantum field theory course, and there we're going to try to make sense out of all these things that we said today. What we want to do in the next 3 lectures is to push unitarity to the limits and see how far we can get in learning what this object is just by using unitarity. Yes?
S is unitary. What is T?
T doesn't satisfy any property that has a name, right? But very good. So for tomorrow, work out what unitarity for S means in terms of T. It will give you an equation, okay? It doesn't have a name, not that I know. So